Hello everybody, and today we're going to be continuing our mathematical series on the topic of differential calculus. Now you might be wondering, why am I only uploading differential calculus? Well, because differential calculus is really important, and it has to do with the rate of change. And I'm not saying that integration is useless, it's also very important. But I like to start with differential calculus. And today we're going to touch about a topic that is very important, and it is the chain rule. Now you see, the chain rule is very important because sometimes it can trick you, and I mentioned that you will most likely get tricked by how the chain rule is used in many ways in differential calculus. For example, if I ask you to get me the derivative with respect to x or dx of say let's say 5x minus 4 to the 6th power. Right? Pause this video and see what you can do. Right now, I'm guessing, if I'm doing this correctly, I'm guessing that you might have applied the power rule, and you might have said that you're gonna bring down the power, and you're gonna say, oh, this is pretty simple. It's gonna be equal to 6 multiplied by 5x minus 4 to the 5th. Are wrong. Well, that is wrong. A huge X. Wrong. Why? Because here you have something that is called a composite function. Now let's go back a bit in time when you were, let's say, I think in 7th grade. You have something called composite functions. Let's write it comp for short. So composite functions. What is a composite function? For example, if I have a function that is, say, the one that we just encountered. I have a function, let's call this function h of x. And it's the one that we have just encountered. So we're going to say 5x minus 4 to the 6th power. Now, can I somehow break this large function into two smaller composite functions and reform it again? It's like how you break a building and then you reform it again. So if I have a smaller function, say g of x, let's say that's equal to, well, I see two functions. I see something raised to the 6th power. So why don't I say that this is a function, this is going to be a function. So let's say that this is nothing but x to the 6th power. And then what's left of h of x? This pal over here. 5x, oh my god, 5x minus 4. So we'll make that another function as well. We'll say that, say, r of x, well, that is nothing but 5x minus 4. Now that we have established this, I also like you to pause the video and see if you can write the notation of this function in a way that you get that output, this output. Alright, so we now know that h of x is equal to 5x minus 4 to 6th power, and we have two composite functions that form up h of x, which is a large function. And I want to differentiate it. I want its derivative. So I'm going to say the derivative with respect to x dx of h of x. Here is where you're going to see the application of the derivative, of the chain rule, So I would like to write this in a notation that would help me know what role does r of x play in the form of h of x, and vice versa, what the role of g of x is in the form, what's its role in forming the function h of x. Well, I can say that h of x is nothing but, in order to raise something to the 6th power, I have to put the base, I have to put the 6th power first, right? And then I have to raise it, right? So you're gonna say this is gonna be equal to, the large one, which is g of x. Hold on. G of, oh, hang on, you can't just write g of x. If you write g of x, you've just written that h of x equals g of x, but that's not true. H of x is equal to g of r of x, because I put g of x, okay, and I say that x is equal to x. g of x equal to x to the 6th power. Okay, what if I replace at each x in g of x with 5x minus 4? Aha, that's true. Because then I'll get, when I replace each x with x in g of x, I'll get that h of x is equal, h of x is equal to 5x minus 4 raised to the 6th power. So then I can write this in a different way. So that means that h of x is equal to g of, g of r of x. R of x. Now this is exactly what you need to figure out to differentiate, because the chain rule now will be applied. So let us just replace h of x with what we figured out. We'll say that this is nothing but the derivative with respect to x, dx of g of r of x. Right, g of r of x. Okay, and let's close that. Hold on, that's for the x and that's for the g, and that's it. You really gotta make sure that you closed all the correct brackets. Okay. Okay, so now what do you take? I like to say this in a way, like, remember in the power rule video or the product rule when I said the prime of 1 multiplied by other? Yeah, I do the same thing here. So what you're gonna say here is, in order to differentiate this composite function, you're gonna say what? The prime of the bigger one, which is g of x, like the first one. So you can say g prime of the smaller one. So you put r of x. Then you multiply it by a prime of the smaller one. So r prime of x, and we can actually write this in the Leibniz notation, because this, in the Lagrange's notation, because this is how Leibniz used to write his notation when differentiating. He used to write the prime sign. This, and if you don't know, I'll give it to you, but you won't see Newton's notation a lot. This is Newton's notation. You just put the symbol, and above it this circle symbol. Because dy dx is the one that's most commonly used. So let's just refer back to it. So this can be written as another way, and some people actually might understand the easy way. So you're gonna say that the derivative of this composite function is nothing but the derivative of the something that's raised, of the something that raises stuff to the 6th power, in this case g of x, with respect to what? So after I differentiate it, with respect to what? With respect to r of x, alright? R of x. And then you multiply it by the derivative of the thing that you're raising the power to with respect to x, alright? So you can say derivative of r of x, alright, with respect to x. Alright, now that you have a nice and basic understanding of what is the chain rule and composite functions, because you're also going to learn on later that you're going to need matrices, you're going to need conic sections, you're going to need series, you're going to need inverse functions, and all of those other things in calculus. So now, I'd like you to pause the video and try to see if you can solve this question all on yourself. Alright, I'm assuming you give it a shot. So let us see, what does this question want? So I have an equation here that describes a relation between y and this. And it says that y is equal to 2x minus 3 all raised to the 9th power. dy dx equals what when x is equal to 8. So we're going to have to notice something. We're not just going to differentiate y with respect to x and get the tangent line equation. No. We're going to figure out, after we differentiate it, what is the derivative equal to when x is equal to e. Okay? Okay, so now let us do this. So we'll say that since y... Okay, I should write since, then, like, the ones that you write in geometry, I guess. Hold on. Okay, sorry. I'm going to say since y equals 2x minus 3 raised to the 9th power, thus dy dx Now you can write this if you'd like to, but in an exam, I personally would write it. So dy dx would be equal to d dx of 2x minus 3, 1 raised to the 9th power, then you put another bracket. Alright, now we can start differentiating. So we're going to say over here that d dx of 2x minus 3, hold on, all of that raised to the 9th power. Sorry. Okay, well, no. Be careful. I have two composite functions. Just like we said, let's form them up. So let's say, for example, that f of x equals the bigger one. It's x to the 9th power. And then I have another function. Let's call that g of x. G of x. And that's equal to the one that's left inside, which is nothing but 2x minus 3. Alright, now that we have this established, can we solve this derivative? And yes, we sure as flip can. Please, YouTube, don't demonetize me. Anyways, so this is going to be equal to, like I said, the prime of the bigger one, which is f of x, with respect to the smaller one. Alright? Now, let us get f prime of x. Hold on. So we can see over here that, okay, hold on, f prime of x. Well, that's just f prime, x to the 9th. So you're going to apply the power rule, and you say that's 9x to the 8th power. And we should also get g prime of x, which will help us. Now, this is something I like to do personally in mathematics and physics question. I always like to write a box where I have everything contained, everything I can contain about this question. So we want to differentiate 2x minus 3. That's pretty simple. You can get g prime of x. Well, you're just going to apply the difference rule, take the derivative of this minus the derivative of this. So this derivative cancels out because it's equal to 0. So 2x, take the 2 outside, multiply the derivative of 1, which is just nothing but 2. Yeah, 2, it's 2. Because, yeah, this is going to be derivative 2x, take the 2 outside, derivative x is 1, 2 multiplied by 1 is 2, minus 0. Yeah, it's going to be equal to 2. Sorry. So now that we have this established, we can easily just plug in everything we need to plug in. Okay, so what is, where'd we go? Yeah, okay. We want to get f prime of x, and we've already solved that. 9x to the 8th power. So why don't we replace each x with g of x? Because we're differentiating f of x with respect to g of x. So now we're going to say it's going to be 9 multiplied by 2x minus 3 raised to the 8th power. Hold on. Does be sure you up to the 8th power. Multiplied by what? By g prime of x, which is the smaller one. And we've already solved that, and that's going to be equal to 2. Multiplied by 2. Now, you can algebraically manipulate this if you'd like to, but we can just simply write in e. Just replace each x with e. And we can solve for this monstrosity. If you solve it, it's actually going to give you a pretty big number. But we'll only take like one significant digit. So we'll say it's going to be 22,361. Let's say 0.17. Now we are on to our second question and last question of the video. So it says over here that from this given equation, a relation between y and something else says that y equals natural log of sine of x, and it wants us to get the derivative of y with respect to x, dy dx, and it did give us a given point. So we're just going to figure out the equation of the derivative, or the tangent line. So as always, pause this video. I encourage you to pause the video and see what you got. Alright, now let's see what we can do here. First of all, you don't need to establish what I always do. You don't see that since y equals that, then dy dx. We can just get straight into it, okay? So we're going to say over here that dx of natural log of sine, sine of x. Hold on, that's the sine, that's the natural log. Guys, you gotta make sure the parentheses, sorry, the brackets. Okay, now as I said, I have two composite functions. Okay, focus carefully, because like a lot of people get scared when they see this form. Even though it's so simple, this one is actually like one of the easiest to differentiate. Like the one we did before over here had a lot of calculations. So okay, so I have two composite functions. Okay. Okay, so let's see. I have sine of x and I have ln of x. Okay, guys. Which one is placed first? Because that's the bigger one. Isn't it ln of x? Too easy, too easy. So that means that, let's say g of x equals natural log of x. And like I said, guys, I didn't say that, but let me see. I might have said it in a different video. Natural log of x, sometimes, like, if you encounter a question, the one who puts the question won't always give you an easy calculus question. So it won't always say natural log of x. Instead, he might say log base e of x. And I'll explain this in a different video why it's like that. Just like log of x, that's log base of 10 and all of that. But as I said, you need to know a lot of stuff in calculus, a lot of stuff before you study calculus, logarithms as well, and inverse functions, so many. Now back to our question. So g of x equals ln of x, and we can say something else over here that, hold on, our other function, let's call that h of x. H of x, well, that's nothing but sine of x. And I really hope that you will be able to pick up on this one. So that means that let's call all of this h of x, okay? Sorry, f of x. So that means that function of x, f of x, well, that's nothing but g, because natural log was placed first. You took the natural log of something, and then you took the sine of x of something, which means that you're differentiating something with respect to something, multiplied by that something with respect to x. Does that make sense? I hope it does. So f of x equals g, which is natural log, g of, yes, h of x. And now we can simply differentiate this. Alright, so we're going to say that, hold on, f prime of x, which is our function, f prime of x equals g prime of h of x multiplied by r, sorry, multiplied by h prime of x. So let us get g prime of x, and all of this will be simplified and will equal to, okay, what is our function g? Well, that's ln of x. What's the derivative with respect to x of ln of x? Natural log of x, 1 over x. Yes, that's correct. 1 over, hold on, replace each x because you're differentiating g of x with respect to h of x. What's h of x equal to? Sine of x. Hold on, 1 over sine of x, that's just the reciprocal of sine of x. Wouldn't that be equal to, sorry, hang on, yeah, 1 over sine of x, trigonometric functions, you have sine, cosine, tangent. Reciprocal of tangent, cotangent. Reciprocal of cosine, yeah. Come on, you got it. Reciprocal of sine is cosecant, okay? So we can replace 1 over sine and simply write cosecant, okay? Cosecant of x multiplied by, hold on, what's h prime of x? So we want to get the derivative with respect to x of sine of x. Well, that's nothing but cosine of x. Cosine of x. And we are done.